Hello, you're welcome to Chemistry with CK. I teach chemistry for O-level, A-level, GSCE and WASI students. Over the course of the week, we've been treating nuclear chemistry. And with nuclear chemistry, we've learned about radioactivity, the types of radioactivity, and the types of radiation given by radioactive substance. In our previous lesson, we learned about radioactive decay. So under radioactive decay, we learn about the three main types of radioactive decay. That is alpha decay, beta decay, alpha decay, beta decay, and gamma decay. Again, we also learned about positron emission and also we learned about electron capture. So before we continue, there is some ambiguity I want to classify. Now, there is this word I've been using interchangeably, which is nuclei and nucleide. Now, these two words, they are not the same, but I use them interchangeably because of the topic we are treating. Now, let me break it down to you. Let's take this substance to be uranium-235. So in this case, when I say uranium-235, here, this is a nucleide. So I can't say that uranium-2 or radioactivity is the disintegration of what? An unstable nuclide. So I'm talking about this whole thing here. Now, when I use nuclei, that means I am moving deeper. So let's assume that this is the uranium-235. And remember, I've told you that every substance is made up of atoms. And every atom contains what? A nucleus. Now, when I say the nucleus, the breakdown or the disintegration is occurring where? The disintegration is occurring inside the nucleus. So when we say radioactivity, this nucleus here is unstable. This nucleus here is also unstable. So as this nuclei breaks down, so this nucleus and this nucleus in plural, we call them what? Nuclei. So when I say a nuclide, I'm talking about the whole thing. But when I say a nuclei, that means that I have moved directly into what? The nucleus. So this was the confusion which I want to rectify. So nuclei here means we are going into the nucleus. And a nuclide here means we are talking about the substance. Thank you, and I hope this clarifies your confusion. So today, we are going to treat what we called nuclear equation. Okay, So we are going to look at nuclear equation. What is a nuclear equation? Now, when we talk about nuclear equation, what we are talking about is a nuclear equation is an expression in symbol, in chemical symbol, which represents a nuclear reaction. So any expression in chemical symbols, to be precise, nucleide, we are talking about nucleide here, which represent a nuclear reaction, is a nuclear equation. Let's look at this, for example, or hypothetically. So this is a simple illustration of a nuclear equation. Expressions here representing a nuclear reaction. Now this expression or every nuclear equation is governed by two laws. So for you to write a good or an appropriate nuclear equation, you must understand two main laws. And the first one is the law of conservation of what? Mass number. When we say the law of conservation of mass number, it means that the sum of the mass number at the left hand side is always equal to the sum of the mass number at the right hand side. 2. The next one which I want you to understand is the law of conservation of atomic number. So when we say conservation of atomic number, it implies that the sum of the atomic number at the left hand side is equal to the sum of the atomic number at the right hand side. So a good nuclear equation must obey those two main laws. So this is what the law of conservation of mass number is saying. A plus E So what we are saying is that the mass number here, these two mass number, A plus E, when you sum them, it must be equal to addition of these two numbers, E plus H. And that is what we mean by the law of what? Conservation of mass number. Again, the second is the law of conservation of atomic number. So what we are trying here is that, or what we are trying to say here is that when you take the atomic numbers, the left hand side, the atomic numbers of the left hand side, when you add them, so when we add them, this place B plus D, it should be equal to what? It should be equal to the addition of F plus H. So a good nuclear equation must always obey these two laws. The law of conservation of mass number and the law of conservation of atomic number. Okay, now let's look at some examples. So what we mean here is, let's look at this, an example of a nuclear equation. And we are being told to find the values of x and y. So how do we do this? What we are going to do here is, when you apply the laws, or you must apply the laws in order for you to find the value of x and y. So if you want to find the value of x, here what we are trying to do is you have to apply the law of conservation of mass number, which is saying that the sum of the mass number here, which is what? 28, is equal to the sum at the right hand side. So this is x plus 4. So making x the subject, x is equal to 28 minus 4. X will give us 24. Again, if you want that of y, you have to apply the law of conservation of atomic number. So 11 is equal to y plus 2. So this implies y will be equal to 11 minus 2, and y will be equal to 9. So x here is 24, y here is 29. Okay, let's look at another example. Okay, let's look at this example. So here, we've been given this nuclear equation to find x and y. So how do we find x and y? For us to find x and y, we must apply the law of conservation of mass number and atomic number. So here, for us to find y, we must know that the sum of the mass number at the left hand side is equal to the sum of the mass number at the right hand side. So here we are having 206 plus what? 2. These are the mass numbers at the left hand side. Is equal to y plus 4. So making y the subject, this plus 2 give us 208 equal to y plus 4. So this tells us that y be equal to 208 minus 4, y will be equal to 204. So we've applied the law of conservation of mass number to find y. If we want x, how do we find x? By applying the law of conservation of what? Atomic number. So here you have x plus 1 equal to 81 plus 2. So here x will be equal to x plus 1 will be equal to 83. So if you want x, x will be equal to 83 minus 1. X is equal to say 82. So this is the law of conservation, or this is the value of x and y. Okay, let's look at the third question. Okay, consider this nuclear equation here. So we're having cobalt 29 plus a deuterium giving out cobalt 60 plus x. Then we are told to find x. So here you could see that we've not given you any mass number and any atomic number. So before you solve, you just have to let us or indicate, okay, let A and B represent the mass number and atomic number of X. So in this case, you, the candidate, must represent the mass number and atomic number by a variable. So here I choose to put A and B there. Now that I've represented the mass number and atomic number by variables, now I can find for X. So now, let's find for A and B. So we are saying that 59 plus 2, which is the mass numbers at the left hand side, is equal to 60 plus A. So now let's make A the subject. So 59 plus 2 give us 61 is equal to 60 plus A. 61 minus 60 is equal to A. This implies A is equal to 1. So in this case here, our A is 1. Now, how do we find B? For us to find B, we must also apply the law of conservation of atomic number. So 27 plus 1 is equal to 27 plus B. So 27 plus 1 will give us what? 28 is equal to 27 plus B. So making B the subject, 28 minus 27 is equal to B. Therefore, B as well is equal to 1. So that is how we solve for question like this. So this means that our A here is 1, our B here is also 1. Okay, let's look at another example. So now let's look here. So as you can see, consider this nuclear equation and we've been told to find y. So like I've always tell you, this y that you've been told to find, represent it by a variable. So now, let's represent the mass number of y by this, the atomic number by this. But you can see that there were some parameters which we didn't give the mass number and atomic number, especially these are what we call the particles. So you must know them. It's a must. You should know that this is what? A neutron. So what is the mass number of a neutron? It is 1. What is the atomic number of a neutron? It is 0. You should know that this symbol here represents what? Alpha particle. So with alpha particle, the mass number is what? 4. The atomic number is 2. So you should know that these particles, they would not be given all the time. So you must always know them. So now, you should know that a proton, which symbol is what? P, is represented by 1, 1, P. Take note. Electron, with the symbol E, is represented by 0, minus 1, E. You should know a positron is also represented by 0 plus 1, E. We also have what? Deuterium, which symbol is what? Small d, is also represented by what? 2, 1, H, should know, or 2, 1, D. So whenever you see 2, 1, H or 2, 1, D, it represents what? A deuterium. Also with proton, we can also say 1, 1, H. Take note. Under nuclear equation here, a proton is represented by 1, 1, what? H. You should know a tritium, which symbol is T, is also represented by 3, 1, H or 3, 1, T. An alpha particle is also represented by 4,2He or 4,2 alpha, the sign. So not all the time we will not be giving you the particles, the mass number and atomic number of these particles all the time. And you should be able to write the equation. So what I want you to know is that these particles, their mass number and atomic number must always be given or must always be known with you as the candidate. So now let's come back to our question. So now, us knowing that the mass number of a neutron here is 1 and the atomic number is 0, for alpha here is 4 and that is 2, we can solve for A and B by applying the laws. So now, all that we need to do is we have to apply the law of conservation of mass number. So here, 27 plus 1 is equal to A plus 4. So now we are going to have 28 is equal to A plus 4. Our A will be equal to 28 minus 4. So A will give us 24. Now if we want B, we must apply the law of conservation of atomic number. So this is going to be 13 plus 0 is equal to B plus 2. So here 13 is equal to B plus 2. B will be equal to 13 minus 2. So this implies B is 11. So our Y here, what will be our Y? 24, 11, Y. Now, when the question asks you the name of Y, you should see that I've already told you that the atomic number is used to identify the element. So now you go back to your periodic table. Which element is number 11? So you start from your hydrogen is 1, helium is 2. So number 11 here is what? It's sodium. So this is sodium 24. However, if the question doesn't tell you to name the element, there's no need for you to. So what we are saying is that you can't be given the particles without their mass number and atomic number. And as a chemistry student, you must know them off head. Now, we can also give you this equation in a word form, which as a chemistry student, you should be able to write our equation for us. So now let's look at this. So now let's look here. So we are having this example. Magnesium 24 captures a proton and produces an alpha particle. So now, how do we write this equation? So magnesium 24 here means Mg with a mass number of 24. Since this is magnesium, you should know that every magnesium is atomic number 12. So captures a proton To capture something means I've told you that when you are captured, that means you are added a proton. Proton here, the symbol is 11p or 11H. So when magnesium captures a proton, it has produced, that means it has emitted what? An alpha particle. So what is an alpha particle? 42He. I've told you that whenever a radioactive nuclei emits a particle, that means that there is a new nucleide formed, which you should always know that there would be a daughter nucleide or a new nucleide formed. So this is how the equation should be. And the daughter nucleide, you should know the mass number. If you don't know, there's a mass number. You represent it by a variable AB. So all that I want you to, you would not be given the equation all the time. Sometimes you would be made to write the equation. Now, after writing this equation, we can now calculate for the mass number and atomic number of our new nuclide to complete it. So here, applying the law of conservation of mass number, we are saying that 24 plus 1 is equal to A plus 4. So here we have 25 is equal to A plus 4. A equal to 25 minus 4. A will be equal to 21. Again, if we want our atomic number, we are going to have 12 plus 1 is equal to B plus 2. So now 13 is equal to B plus 2. Therefore, this means B will be equal to 13 minus 2. And this implies B is equal to 11. So this here means that our A is 21 and our B is 11. So you would not be given the equation all the time. So all that you have to understand, like our previous lesson, I told you that when you capture, you are adding. When you are decaying, you are producing. Or when you are emitting, you are producing. So whenever you hear capture, you are going to add it to the left hand side. Whenever you hear emit or decay, it will come at the right hand side. Let's look at our last question and move on. So now, our next question is lead 208. So lead, what is the symbol of lead? That is Pb. And the 208 here represents the mass number of the lead. So you should know the atomic number of lead, which is what? 82. So now, this lead captures 2 alpha particles. So lead plus 2 alpha particles. And after it capturing 2 alpha particles, it has released, or it releases what? it releases 3 protons. So 3 protons are being released. So whenever I told you that there have been a release, that means that a new nuclei has been released together with what? 2 or 3 protons. So now, how do we solve this question? You should know the mass number and atomic number of these particles. So you should know that whenever there is an alpha particle, the mass number of this alpha particle is 4, the atomic number is 2. And whenever there is a proton being released, you should know that the mass number of a proton is 1, the atomic number too is 1. Now, this new nuclide form will be represented by what? A variable A and B. Any question? So now, what we are saying is we have to find A, then we have to find B. How do we do that? We must apply the 2 laws. So now the law of conservation of mass number here is 208 plus, there is 2 here. So 2 into bracket multiplying the 4, which is the mass number, equal to what? A plus 3 multiplying the mass number here, 1. So now we have 208 plus 8 is equal to A plus 3. So now making A the subject, we are going to have 216 is equal to A plus 3. So here A will be equal to 216 plus 3, and A will give us 21 minus 3, and A will give us what? 213. Now, with our lead here, so we are going to have what? 82 plus 2 by 2 equal to B plus 3 times 1. So here, we are going to have 82 plus 4 is equal to B plus 3. So this is going to give us 86 is equal to B plus 3, and B will be equal to 86 minus 3, which will give us 83. So all that I want you to know is that sometimes you'll be given in a word format to write the equation. So after writing the equation, you should know how to interpret. So this tells us that this is 83 to 13. Okay, thank you. Now we are moving to a next topic, and this next topic is we have some nuclear equations that can be written in the condensed form. Now remember when we started nuclear reaction, we said that we have artificial radioactivity. And what did we talk about artificial radioactivity? We said that under artificial radioactivity, a nuclide is being bombarded with what? A particle. And when you bombard a nuclide with a particle, it becomes what? Unstable. And as it disintegrates, it will give out radiation and what? Energy. Now, most of the artificial radioactivity can be written in the condensed form as well as in the expanded form. So let's look at this. So what we are saying here is, under artificial radioactivity, we said that you are bombarded. So when I have an unstable nuclei, let me call this my this my nuclide P. Or let me use T. This is my nuclide T. Now under normal circumstance, this nuclide here wouldn't have emitted radiation, or is not a radioactive substance. But for me to make this T give out radiation, I will bombard it with a particle. That means I'm coming to add B to T. So when I add B to T here, what happens? What will happen here is that now the T will become unstable and it will disintegrate, give you out a radiation. So the radiation given here, let me make it E. Remember, I told you that whenever a radiation or a particle is given out, it tells us that a stable nuclide is formed. So let me call this stable nuclide P. So let me make it simple for you. So this, let me call this the parent nuclei. Remember that this is the parent nuclide. And the B here is the particle you are going to hit. So we call this the bombarding particle or the injecting particle. That is our B. Now, the E here is what? Our particle which is ejected. Let me see, the P here is our daughter nuclide form. The daughter nuclei. We can also call it the product. The product nuclide. And our E here is our ejecting particle. All that I'm trying to say is, whenever you have any nuclear equation in this form, you can write it in a condensed form or a more simpler form. All you have to know is that you see the left hand side is having 2 and the right hand side is having 2. But I've told you that you must know the particle. So how do we write this type of nuclear equation in a condensed form? So equations in this form here can also be written in a much simpler form. How do you write it? You see this parent nuclei, this T here. We will write it T, which is the parent nuclide. The T represents the target nuclei. But I'm trying to simplify it for you. But the actual word for the T here is the target nuclei. Now, I will introduce a bracket. The bracket here, this particle, this binding particle, which you are coming to add to it, will be put here. That is your P. Now, you introduce a comma. You close the bracket. Now, the daughter nuclide, which represents the product nuclide, is always outside. This is P. And the particle which is ejected is written inside here. So the T, we call the T the target nuclei. Or target nuclide. Now I can use it interchangeably since you understand. The B here is the binding particle or the bombarding particle. So the particle which are going to bind or bombard is our B. The E here is our ejecting particle. And the P here is the product nuclei. So you should know that nuclear equations in this form can also be written as this. In that same sense, we can give you this to write it. So we mostly call this is the expanded form. And this is the condensed form. So when I give you a condensed form, you can write a condensed form to an expanded form. And you can write an expanded form to a condensed form. Now, when you are given a condensed form, to write it to an expanded form is very simple. Just use your pen and just use a short dash. Separate this by short dash. So separating this by a short dash here, you are done. So now this is going to be T plus P giving us P plus E. So mostly nuclear equations in this form, mostly they are artificial radioactivity, can be written in the condensed form. So let's look at how you can write a condensed form to an expanded form, and also how to write an expanded form to a condensed form. Okay, so now this is an example of what? A condensed form. How do you write this expanded, this equation? So all that I've been telling you is just use a short dash. Separate this. So this nuclide here is your target nuclei. This P here is your binding or bombarding particle. This O here is your product nuclei. And this alpha here is your what? Ejecting particle. So when I separate this, now it means that nitrogen 14 N40 has been bombarded plus P. And I've told you that you must know that P represents what? A proton. And when it's being bombarded by P, this product is being produced. O, oxygen 15H, and this particle here, this radiation here is being emitted. So now, remember this equation given is not complete, so you must complete it. Completing it here means that the proton here, the mass number of the proton is 1, the atomic number is 1. This is an alpha gamma radiation, so the mass number is 0, the atomic number is 0. So you can see that a condensed equation has been expanded. So you should know that always this is the target nuclei. Take note, target nuclei. This here is the binding or bombarding particle. This here is your ejecting particle, and this one here is your product nuclei. Okay, let's look at another example. Okay, let's look at this. We've been given a condensed nuclear equation, and we are being told to balance. Balance here means that we have to expand it. So how do you expand it? All that I'm saying is that you have to separate this with your simple short dashes. Then now you write. So here we are having what? We are having aluminium 27. Okay. Now our bombarding particle here is N. So plus N, giving us, this is our product nuclei, which is X, plus this one here is our ejecting particle, which is what? Alpha. I've told you that these particles, you must know their mass numbers and atomic numbers. So neutron is what? 1, 0. This alpha here is 4, 2. So this tells us that the mass number and atomic number of the product particle is unknown. So here you are going to represent it by a variable a and b. Then you solve for a and b. So now let's solve for a and b by applying what? The law of conservation of mass number and atomic number. So here we are going to have 27 plus 1 is equal to a plus 4. So now 28 is equal to a plus 4, and a is equal to 28 minus 4 equal to a. Therefore a will be equal to 24. Now if we want b, 13 plus 0 is equal to b plus 2. So here 13 is equal to b plus 2. b will be equal to 13 minus 2, and this will give us 11. So this tells us that a is what? 24. B is what? 11. So this is the nuclear equation balanced. So we were given a condensed equation, then we needed to balance it by expanding it and finding the value here. So this tells us that this here is 24 and this here is 11. Okay, let's look at another example, then we continue. So we are being told to balance this nuclear equation. So how do we do it? I've told you that you just have to divide this by 2. So this tells us that this is X plus what? Our binding particle here, P, giving us, this is our product particle, our product nuclei carbon 12 plus our ejecting particle alpha. So now, how do you balance it? Just substitute the mass number and atomic number of the particles. So the mass number here is 1, the atomic number here is 1. Again, the mass number here is 4, the atomic number here is 2. I've told you that these particles, you must know the mass number and atomic number. So for us to balance here is now x. So you have to represent the mass number of x by A and B. Then you solve for A and B. So here, A plus 1 is equal to 12 plus 4. So now, A will be equal to what? So A plus 1 is equal to 16. So if we want A will be equal to 16 minus 1. This implies A is 15. And we are done. Now for B plus 1 is equal to 6 plus 2. So B plus 1 is equal to 8. B will be equal to 8 minus 1. And B is equal to 7. So this tells us that our A here is 15. And now B here is 7. And we balance the equation. So we can give it to you in a condensed form. Also, we can also give it to you in an expanded form. Now, let's look at the other way around. When we are giving an expanded form to convert it to a condensed form, how do we write it? Okay, so we can also be given this equation. Remember, I've told you that this equation here is an expanded equation. Now, we want to convert this expanded equation to a condensed form. So you must always know the particles by now. So how do you write? So you should know that this one here is our nuclei, the parent nuclei. So I've given you examples of the particles. So please note them. So this here is B, which is our target nuclei or the parent nuclei, which is B11,5. Then you introduce your bracket. This is what? 1,1H. Remember, I've told you that this 1,1H here represent what? A proton. So you just write B, you put your proton inside, comma, to bring a comma. Now, for now, let's close the bracket. So this boron here has been bombarded with a hydrogen, a proton, to produce. Now, what comes this side here is always the daughter nuclei or the product nuclei. So here, what is here? Be84 always is outside the bracket. Now, this is your particle emitted, alpha particle. The alpha particle comes inside. So that is how we convert an expanded to a condensed. Okay, now let's look at another example. So we've been given this equation to write the condensed form. So always your target nuclei, nitrogen 14 here, is always outside. So 14 nitrogen. Then you introduce your bracket. Then this binding particle, which is N. Now when you are writing the particle, you don't bring the mass number and atomic number. Take note. Comma. Then you close your bracket, leaving a space here. What comes here is your product nuclei, your daughter nuclide form. So here our daughter nuclide form is 14, carbon 14. And you should know that this is a particle which is being emitted. And what particle is this? That particle here is a proton. So you must take note of what is being emitted. So we've converted what? A stable nuclei to a daughter nuclei. Sorry, an expanded equation to a condensed equation. Now, let's look at something. Let's assume that we have 210N here. Let me take it like this. So now, let's assume we are having this. How do we write it? We are going to follow the same procedure. So now, here, our target nuclei will always be N, which is nitrogen 14, 7. Now, this is our nitrogen 14, 7. We are saying that it's been bombarded with what? 2 neutrons. So here, you are going to write your binding or bombarding part. Here is 2N, a comma. You leave a space, you close it. So here, what product nuclei has been formed? Our product nuclei is carbon 15. Then this particle here is what? Is a P. So whenever there is a coefficient in front of the particles, you must introduce them in your condensed form. Thank you. Okay. So ever since we've started these topics, I've seen students asking me, say, how will you know that a nuclide is radioactive? So we want to look at the factors that affect the stability of a radioactive nuclei or a radioactive substance or a substance. So factors affecting stability. Now, what we are trying to say here is we want to look at how or what makes a nuclide stable or unstable. Now, it depends on 2 main factors. I repeat, 2 main factors. The first factor is the neutron to proton ratio, represented by the N/Z. So for a neutron, for a nuclide to be stable or unstable, is going to depend on the neutron to proton ratio. I will explain. 2. The next factor is what? The binding energy. E. Now, these are the two main factors that affect the stability of a nucleus. However, sometimes there are certain questions that you must apply the half-life. Take note. Whenever we ask you state 1, it should be one of these. State 2 should be these two. But when you are told to state 3, then you can add the half-life. So, if a nuclide will give out radiation, what are we saying? What we are trying to say here is, it is going to depend on 1, the proton to neutron ratio. 2, the binding energy. Then, if we need to carry on, we can add the half-life. I will explain. But on the more important note, there are two main factors. That is the neutron to proton ratio and the binding energy. Okay, so we are going to take the binding energy, the neutron to proton ratio, then explain. Now let's look here. When we say neutron to proton ratio, we all know that every nucleus, when you take the nucleus of an atom, you are going to have what? The protons and the neutrons. So let's assume that this is our proton and this is what? Our neutron. Now, the ratio, the amount of proton and neutron here causes the nucleus to be unstable. How do you explain? Now, the proton here, we all know that the proton is what? Positively charged. Positive. The neutron here is neutral. So now, we are continuing. If I have a nucleus like this is positive and this is positive. Now, when these two positive comes closer, what happens? There would be a repulsion. So what we are saying is that the protons create repulsion. Now, so what will prevent these two protons from repelling? So now if a neutron is here, the neutron is like the glue, the nuclear force, which is holding the protons or preventing the protons from what? Repelling. So here we are saying that yes, the protons are positive, the neutrons are neutral. So if you have any nucleus and there are more protons, what is going to be? There will be a lot of repulsion. And when there is a lot of repulsion, then the nucleus becomes unstable. But what we are saying is that the neutrons there is gluing them. It's a nuclear attraction, attracting the protons. That means it is preventing the protons from what? From repelling each other. So what we are saying is that if the ratio of the neutrons and the protons If there are more protons than the neutrons, what will it be? There will be more repulsion. And if there are more repulsion, the nucleus will be what? Unstable. So what we are trying to say is that the neutron to proton ratio. Now in chemistry, if the neutron to proton ratio is approximately equal to 1 for lighter nuclei. Okay, now I have to explain some terms for you here. In chemistry, we call some people lighter, and nuclei being lighter nuclei. Whenever I say lighter nuclei, it means atoms with atomic number less than or equal to 20. So from hydrogen to calcium, we call them lighter nuclei. So from hydrogen, helium, lithium, beryllium to calcium, they are all classified under radioactivity. We call them lighter nuclei. Now heavier nuclei are those with atomic number greater than 20. So from scandium to the 180, we call them heavier nuclei. So whenever we are talking about the proton to neutron ratio, when you come to lighter nuclei, those that are having the atomic number less than what? 20. Their proton to neutron ratio must always be approximately equal to 1. So if it is 1, it means it is stable. If it is greater than 1, it tells you that that nuclide here is what? Unstable. Let me use an example. So now, let's take a lighter nuclei. A lighter nuclei like carbon. So now I'm taking carbon 12. So we can see that this carbon 12 here, what is the number of protons here? The number of protons here is 6. And the number of neutrons here, 6 minus 12, which is what? 6. So what do we find the proton to neutron ratio here? So N over say P. So 6 on 6. Here we are going to get 1. So this means that this nuclide here is stable. So those, you can see that carbon is having atomic number say less than 20. So it's a lighter nuclide. For those who are lighter nuclei, for them to be stable, the proton to neutron ratio should be approximately equal to 1. So any lighter nuclei which has its neutron to proton ratio greater than 1 is unstable. Now, let me look at this. Carbon, say, carbon 14. Now, carbon 14 here is a lighter nuclei. Remember the atomic number is less than what? 6. So the proton here is 6. Now, what will be the neutron? The neutron here, 6 minus 14, which is what? 8. So 6 minus 14 is 8. So what will be the neutron to proton ratio? So the neutron to proton ratio here, you're going to get 6 on what? 8 on 6. So 8 on 6 here is what? One whole number, that is 2 on 6. So 1 on 3. So when you try to do it, you are going to have your ratio to be 1.333. So here we are having a lighter nuclei, 1. And this lighter nuclei, the neutron to proton ratio is greater than 1. So this means that since the neutron to proton ratio is greater than 1, it means that this nuclide is unstable. So we use the proton to neutron ratio to determine whether a nuclei is stable or what? Unstable. Now, for a heavier nuclei, so here we are saying that when it's a lighter nuclei and the neutron to proton ratio is approximately 1, it is stable. If it is greater than 1, means that that lighter nuclei is what? Unstable. That means it can disintegrate and give out radiation. So now, for a heavier nuclei, remember that I've told you that heavier nuclides have the atomic number greater than or equal to, say, 20. Now, for those people which are greater than 20, for you to be stable, your neutron to proton ratio must be approximately equal to, the neutron to proton ratio must be approximately equal to between 1.1 to 1.4. If you are greater than 1.4, that means from 1.5 going, your nuclei is what? Unstable. So what you are saying? So now, those which the neutron to proton ratio is greater than 1 is from 1.5 going are usually unstable. For example, uranium-235. So here you can see that the proton here is what? 92, and the neutron here is what? 143. So the neutron to proton ratio here, 143 over 92, is equal to, I think, approximately equal to 1.54. So since the neutron to proton ratio is 1.54, it tells you that this nuclide here is what? Unstable. So one thing that you have to know here is that for you to know that a nuclide is unstable, we can use the neutron to proton ratio. In as much as we can also use the band of stability, which we don't want to go there at our level. So all that I want you to understand here is, 1, if the neutron to proton ratio of a lighter nuclei is greater than 1, that means that nucleus is what? Or that nuclei is unstable. If the neutron to proton ratio of a heavier nuclei is greater than 1.4, that means that the heavier nuclide also is unstable. So for us to know whether a nuclei is stable or unstable, then we are going to look at the neutron to proton ratio. So in summary, this is what I want you to remember. So in summary, the neutron to proton ratio, if that nuclei is a lighter nuclei, the neutron to proton ratio must be equal to 1 or approximately equal to 1 for it to be stable. So if it is greater than 1, then it means that nuclei is unstable. For a heavier nuclei, For it to be stable, the neutron to proton ratio must be between 1.1 to 1.4 approximately. But if it is greater than 1.5, it tells us that the heavier nuclide is what? Unstable. So one way that we can say that a nuclei is stable is the neutron to proton ratio. Again, we have another factor which we are going to talk about here is the binding energy. Now, sometimes we can say the binding energy per nucleon. Yes, they are slightly different. But let's work from the binding energy and bring it down. Now, let's go back to the nucleus. Now we are having the protons. We are saying that within the nucleus, we have what? We have the protons and we have the neutrons. So in physics, or let me say, there is a force holding these particles together, and that force we call it binding energy. Now, the protons and neutrons collectively combining the two, we call them what? Nucleon. So when we say the nucleon binding energy, we are talking about what? The force holding the nucleon together. So that force here is what? Is the binding energy. So if you want to break a nucleus, if you want to break a nucleus and you apply a high energy, that means that the binding energy there is high. Now let me take this pen and let me say I'm trying to break it. If I want to break this pen, I must apply a high amount of energy. Why am I applying a high amount of energy? Because the forces here are hard. So when we talk about binding energy, we are talking about the energy holding these nucleons together. If this energy there is high, that means the nucleus is what? Stable. So if we have a high binding energy, it tells us that the nucleus is stable or the nuclide stable. So what we are saying? So if I take this thing, now if I take something like this and now apply it, I've seen that it has break. This tells us that the nucleus, the binding energy is weak. This nucleus can easily break. And that tells us that since it can easily break, then it implies that the binding energy there, the energy holding the nucleons together is weak. And since it is weak, it means the nuclide there is unstable. So low binding energy implies what? Nuclide is unstable. So what we are going to do here is, yes, binding energy, the force or the energy holding the nucleons. When you say nucleons, we are talking about the protons and neutrons. So the force holding the protons and neutrons together is the binding energy. So if this energy here is strong, that means that the nuclei is stable. But if the energy there is weak, that means that the nuclei is what? Unstable. Now in physics, you will be calculating the binding energy. So Albert Einstein, in its theory of relativity, developed a formula in calculating the binding energy, which is equal to what? The mass defect times the speed of light, which you are going to do that in physics. In chemistry, all that I want you to understand is, for a nuclide to be stable, it depends on the binding energy, the energy holding the protons and neutrons together. If this energy is high, then it tells you that the nucleus or the nuclei is stable. If the energy is low, it also implies that the nuclide is what? Unstable. One may ask, how will you know a nuclei is high? How will you know a nuclei is low? You are going to do that in physics. For you to know a nuclei is high or the binding energy is high, then that means that it must have a larger mass defect, which you are going to do that in physics. We are not going to do any calculation here. For you to know that a nuclide or the binding energy is low, then it implies the mass defect is small. You will learn about mass defect when you are treating physics. But in the natural sense, like if I want to tell you about mass defect, the binding energy is equal to the mass defect times the speed of light. So this mass defect here, okay, let me try and bring it down. So the mass defect, Albert Einstein saw that the total mass of the nucleus, when you weigh it, and when you take the individual protons and neutrons and you weigh them, there is a change in mass. The masses are not always the same. So if I take this whole thing here and I weigh, then I now take the protons alone, I weigh them. Then I now take the neutrons alone and weigh them. When I add these two and I compare it to the total mass of this nucleus, it is never the same. And that change between it is what we call mass defect, which you do that in physics. So now, if a nucleus is stable, one, it will depend on the neutron to proton ratio. Two, is going to depend on what? The binding energy. Please take note. I've told you that there are only two factors. However, sometimes we can ask you questions involving half-life. So please, half-life is not a factor when considering the stability of a nucleus. But sometimes we involved it when talking about stability of a nucleus. So I will go further and explain what we mean by half-life. Yeah. So now half-life. What do you mean by half-life? Sometimes someone will say that a life that has been slashed into two. Yes, you might be correct, but when we say half-life, we are talking about the time that is taken for a radioactive nuclide to disintegrate. So now if I have a nucleus here, I want to measure the time that is going to take this nucleus to become half. So let's assume that this is full, right? This is 1. So the time that we will need, or the time this full thing become half, that time, we call that time half-life. Is the time taken for half a radioactive nuclei to disintegrate. So the time taken for a radioactive nuclei to disintegrate, to break down, to have its original amount is what we call the half-life, the time. So half-life is a time. So now, let's look at this. Let's assume that you are 2 people, and these 2 people, you've gone and meet a fetish priest. Sorry, let me use that. And now you've been told that A, you are going to have, or you are going to take 3 years for you to go and see your maker. So now the 3 years is your half-life. So your T half is 3 years. So A has a half-life of 3 years. Then we have B. B, you there, you went. And they'll tell you that you there, you are left with 6 months. That's 6 months. So which of these 2 will be stable? In natural science, you know that the one with a longer half-life is more stable. Will be stable. I'm okay. I have nothing to worry. But the one whose half-life is shorter now is unstable. So all that we are trying to say is that when the time at which you are breaking half, that means that if I have A, every 3 years, so if you have 3 years, A will be left with half. Another 3 years, what will be A left? Left with a quarter. So you keep on breaking it half. That is what I mean by half-life. Now when you come to B, what happened to B? With B, B will break down in 6 months. Another 6 months, and B will left. So what we are saying that in terms of half-life, the shorter the half-life, the more unstable you are. The longer the half-life, the more stable the radioactive nuclei. So what are we trying to say here? All that we are trying to say here is that for you to know whether a substance, a nucleide, let me put it that, a nucleide is stable or unstable will depend on the neutron to proton ratio, which we've talked about, the binding energy, which we've also talked about, again, the half-life, which I've told you that mostly use it to ask a question. So there are 3 factors that determines the stability of a radioactive nuclei. 1, half-life. 1, neutron to proton ratio, and 2, the binding energy per nucleon. Now, to wrap things up, we would want to review all that we've done today. We've looked at nuclear equation, then we've looked at how to write them, how to calculate them. Again, we've looked at a condensed form, mostly for artificial radioactivity. Then we've also looked at factors that affect radioactivity, which you must know and understand to explain. So we said that neutron-proton ratio, when the nuclei is lighter, the neutron to proton ratio should be 1 for it to be stable. So if it is greater than 1, it means the nuclide is unstable. And if it is a heavier nucleus, if it is greater than 1.5, it implies the substance or the nuclide is unstable. 2. The binding energy. If the binding energy is strong, it means the nuclide is stable. If the binding energy is weak or low, it means the nuclide is what? Unstable. And you'll be doing a lot of calculation for binding energy with or in your fixes. And the third here, which we mostly included, is the half-life, which we are saying that the longer the half-life, the more stable the nuclei. The shorter the half-life, the less stable the radioactive nuclide. Please subscribe to my channel, like and share, and you can comment if you have any question. Just remember to tell a tired soul that God is alive. Thank you and see you once again. Bye-bye.